In Lecture 29, we shift our focus from the subatomic world of the nucleus to the largest continuous objects in the universe, the luminous objects that we call stars. You know, in spite of the extreme difference in scale, this is a really logical segue, for stars are essentially giant nuclear fusion reactors. Indeed, for many astronomers, the most important principle associated with astronomy is that stars are giant nuclear fusion reactors. But, you know, I want to take a slightly different tack and focus on the nature of astronomy itself. The fact is that most people love astronomy. The heavens are endlessly fascinating, and they've captivated humans since long before recorded history. But few people realize that astronomy is the science, and indeed the art, of collecting and analyzing and interpreting photons from space. I'm going to begin this lecture by focusing on the nature of astronomical data. So what are astronomical data? What can we learn from them? How are the data collected by telescopes? What great instruments are now in use, and what even grander devices are being planned for the future? And then, and only then, I'm going to examine the nature of stars. Our study is going to be greatly enhanced by the simple and the elegant Hertzsprung-Russell diagram, which reveals that most stars obtain their energy by the fusion of hydrogen. Let's begin then by considering a connection between the last lecture and this one. Nuclear fusion reactions are the process by which two hydrogen nuclei combine to form a helium nucleus, plus a lot of energy. In this process, approximately 0.6% of the mass of hydrogen is converted into energy. This is a direct illustration of Albert Einstein's equation, energy equals mass times the speed of light squared. Astronomers tell us that stars are natural fusion reactors, but how do they know that? You know, we can't go and sample the sun. We can't send probes to return data from its atmosphere. Indeed, based on what we understand about material properties, there's no conceivable way a human explorer could ever approach the sun or any other star. So how can scientists say for sure what's going on deep inside a star? To answer that question, we first have to examine the nature of astronomical data. Astronomy, it's an observational science, and virtually all the information that we have about distant stars comes from photons. That's all the different kinds of electromagnetic radiation. Those are waves of energy that travel 186,000 miles per second through space. And the art of astronomy is the collection and the analysis and the interpretation of these data. So what exactly are astronomical data? Astronomers measure photons. Those are individual quanta of electromagnetic radiation. Recall the nature of photons. All photons can be described as waves. Those waves travel 186,000 miles per second. And photons come in all different wavelengths, from those very long radio waves to short gamma rays and everything in between. Microwaves, infrared radiation, visible light, ultraviolet radiation, and X-rays. And in particular, astronomers measure at least 5 different aspects of photons coming from space. They measure their wavelength or their frequency. Remember, those parameters are closely related to each other. As wavelength gets longer, the frequency becomes higher and the energy increases as well. And then a second parameter is the intensity. That's basically a measure of the number of photons coming to us. We can also look for the direction of the photons, see where they're coming from. A fourth property is called polarization. That's the orientation of the waves, and I'll show you that in a bit. And then the variation of all these parameters with time is yet another parameter you can look at. So let's look at these 5 parameters in more detail. The wavelength of photons from space is measured by spectroscopy. In a spectroscope, there's a prism or a diffraction grating, and it breaks the light into a spectrum of different wavelengths, what are in effect different colors. At least 3 different kinds of spectroscopy are used in astronomy. There's emission spectroscopy that measures light from luminous objects like stars that are emitting light. And then there's absorption spectroscopy that measures light that's passed through some partially transparent matter like a cloud of gas in space. And finally, there's reflection spectroscopy. That's by which astronomers measure light that's reflected off the surface, especially of planets and asteroids and other objects that don't glow. So then the intensity of light from space is measured by a device just like a light meter that you use in photography. You count photons, and you do this by taking advantage of the photoelectric effect. As photons fall on a photoelectric material, that material produces an electric current, and the current is proportional to the number of photons. The very best photoelectric materials can detect single photons coming from across the entire visible universe. And then you measure the direction to an astronomical object, and that's done by measuring two angles. Remember the demonstration in the very first lecture? You can use a compass and a protractor, and first thing you do is you take a compass, you see an object in the space, and you measure the heading to that object with a compass. So that's just a compass heading. And then the second thing, you measure the angle up to the object, for example, using a device just like a protractor, and you can sight up through the protractor, and there's an angle that corresponds to the vertical angle up to the object. So in principle, this is a pretty straightforward process. You can make this kind of measurement for stars and planets, albeit rather crudely, with nothing more than these tools. But astronomers take these position measurements very, very seriously. Recall the importance of Tycho Brahe's improved measurements. They led directly to the rejection of both the Ptolemaic and the Copernican models of the solar system, which had circular orbits. Kepler used that data to derive his laws of elliptical planetary motion. And we'll see that precise position measurements, that's the field of astrometry, is still very, very important. Then there's polarization. Polarization is an intriguing aspect of light that I haven't talked about yet. To show you this phenomenon, I'm going to go back to my favorite telephone cord. And you see, you can wave a telephone cord in a couple of different directions. A wave that arrives at Earth can have many different orientations, just like this wave. So you could have a vertically oriented wave, or it could be horizontally oriented like this, or sometimes waves just come in all sorts of random orientations every which way. Now you can determine the orientation of a wave by using a polarizer, and you've probably had the experience using polarized sunglasses. Take your polarizing sunglasses and change the orientation. You see the polarization blocks out certain orientations. So astronomers determine the polarization of light from distant star by looking at the star and rotating the polarizer and seeing how the intensity of light varies as you rotate the polarizer. And finally, astronomers document the variation of all these other parameters, that is wavelength, intensity, position, and polarization, with time. Now, given how fixed the heavens may appear to be when you go outside, it's amazing how variable various astronomical objects can be. But to document these changes, indeed to measure all the various attributes of heavenly objects, we need to obtain measurements of ever greater accuracy. Well, once we make all these measurements, what can we learn from the data? Astronomers use observational data to understand the universe. Basically, they want to know the spatial distribution of objects, the dynamic state of these objects, and the history and the future of the universe and its contents. So one of the greatest challenges in astronomy is that the universe is three-dimensional. And yet we see the stars almost entirely in two dimensions. Think about that. The universe is three-dimensional, but we see it as a flat black surface speckled with little lights here and there. So what can we learn about stars? It turns out that astronomers try to obtain at least 6 key pieces of information. First, very important, is distance. The distance to relatively close astronomical objects can be measured by parallax. That's a form of triangulation. As the Earth swings from one side of the sun to the other over a 6-month period, we get slightly different perspectives on the heavens. You can duplicate this just by swinging your head from one side to another, and relatively close objects appear to move against the background of more distant objects. Now the problem with this method is that the distance gets very, very large compared to the diameter of the Earth's orbit. The apparent movement of a star gets smaller and smaller, and eventually that motion is just lost in the fuzz that's imposed by the resolution of telescopes. So today, even with high-powered telescopes and satellites, triangulation can only be used to distances of about 600 light years. That's just a mere hop, skip, and a jump on the cosmic scale. So on beyond parallax, astronomers use a variety of objects called standard candles. They have known brightness. The total energy radiated by these objects is known by one means or another. So a 100-watt light bulb, for example, that's a splendid standard candle. If we see a bulb that's far away, then by comparing the amount of light we receive with the known amount radiated by a 100-watt bulb, we can determine how far away that bulb is. This calculation involves working out how far away the object would have to be for the light to be diluted by the measured amount. The astronomical distance problem then comes down to finding the equivalent of 100-watt light bulbs in the sky. Now, the second characteristic of stars is their composition, and as it turns out, nature has given us a fabulous way to measure the elements that are present in stars. In fact, the composition of a star can be determined from emission line spectra, the bright line spectra of the elements. Every element has its own distinctive suite of emission lines. So it's pretty easy to determine the composition of stars. By the way, the element helium, that was first observed in the emission spectrum of the sun. And then a third characteristic of a star is its motion. And there are a couple of different aspects to it. There's the absolute side-to-side motion of a star. That can be deduced by careful observations of a star's position over very long periods of time. It's also possible to measure whether a star is traveling towards us or away from us by using what's known as the Doppler shift of light. I'll talk more about this in a few lectures. Suffice it to say that if a star is moving toward us or away from us, the characteristic wavelengths of hydrogen and other elements are going to be shifted either to the blue end or the red part of the spectrum. And then the fourth characteristic, that's the surface temperature of a star. And that's basically determined from the star's color. You've probably noticed how the color of hot objects reflect its temperature. So a relatively cool fire glows at sort of a dull red-orange. And at hotter temperatures, a fire can appear yellow. And a very, very hot blowtorch, that can actually appear to be blue-white. Well, there's a technique called optical pyrometry that allows you to determine an object's temperature from its glowing color. And that's basically what astronomers do. They measure the relative intensity of different colors, reds and blues and so forth, coming from the hot star. Now, there's another critical property of a star. That's its total energy output. You know, it's not usually possible to measure this parameter directly. What you have to do is measure the brightness or the apparent magnitude of a star. That's to measure the number of photons reaching Earth. And that information, combined with the knowledge of the star's distance, that gives the total energy output of a star. To get a better handle on this idea, think about light coming from a candle versus a campfire if you're in the woods at night. The total intensity of light you see depends both on the size of the flame and on its distance. And then finally, astronomers want to know the mass of a star, and that's not always possible. But sometimes the mass can be deduced in part from a star's motion. This is easiest when the star's in a binary system. That's two stars that orbit around each other. If you can measure the distance between two stars and you see their relative motion, you can get a really good idea of the mass of both stars. Still, the primary technique for determining the mass of stars is from theoretical models. Okay, I reviewed several kinds of astronomical data and 6 of the ways that those data are used to understand stars. But there's one more basic aspect of astronomy that I need to cover. How are the data collected? So the astronomer's principal tool is the telescope. Now, telescopes in the most general sense are devices that collect electromagnetic radiation from distant sources. They're photon collectors. And that covers the entire electromagnetic spectrum, not just visible light. You've undoubtedly seen many photographs of remote observatories in the West, in Hawaii, in South America, in Australia, and so on. You know, telescopes are so important that the science of astronomy has advanced hand in hand with the development of new telescopes. And of special note in this regard is the development of a whole fleet of orbiting observatories. These are high above the atmosphere. See, the atmosphere distorts visible light, and it's completely opaque to many ranges of wavelength in microwave, infrared, ultraviolet, X-rays. It's opaque. So now, for the first time, we have orbiting observatories to study all of these wavelengths. Indeed, many astronomers refer to the present as the golden age of astronomical observation. Think about these different wavelengths. Now, optical telescopes, that uses visible light. And here's how it works. Optical telescopes use a combination of lenses and mirrors. In this refracting telescope, there's a sequence of lenses, an objective lens and an eyepiece. Light comes through, it's bent through the objective lens, through the eyepiece, and comes to your eye, and that magnifies distant objects. Now, the first person to use the telescope for astronomy was Galileo Galilei. Upon hearing of the telescope's invention in Holland, that was in 1609, he was the first scientist to use it in astronomical studies. He built several of his own refracting telescopes, which used that series of lenses, and one of his first telescopes achieved a magnification of 30 power. Recall his amazing discoveries. He was the first person to see craters and mountains on the moon. He saw phases of Venus, the moons of Jupiter. He saw something that was related to the rings of Saturn. He saw sunspots, countless stars that were invisible to the unaided eye. Anyone could have done this. Galileo was just unusually open and receptive to these unexpected aspects of the heavens. Now, there's another kind of telescope, a reflecting telescope that uses a curved mirrored surface to concentrate light. Here's how that works. You have a mirror, and the light comes in, it bounces off the mirror, and is concentrated again through an eyepiece into the eye. Now, because glass is heavy, a thin mirror can be made much larger than a solid lens. The largest telescopes today thus use mirrors, sometimes more than 25 feet in diameter. These are amazing. They're beautiful machines. They capture photons from the most distant places in the visible universe. There's a new technology. This allows these mirrors to be made on a giant rotating furnace. The furnace melts the glass and it spins it into a perfect parabolic shape. These large mirrors are very expensive, but they collect a lot more photons than the refractor telescopes. And now there's a way to make even larger telescopes, potentially as large as you can imagine, by using lots of little mirrors. These multiple mirror telescopes are a lot cheaper in terms of the glass, but they require much more sophisticated and expensive computer-controlled alignment. Now, the best astronomical observatories are constructed at very high elevation. They're far from the light pollution of cities. And important observations include the Keck Observatory on Hawaii, and there's a cluster of observatories in the high mountains of Chile. It turns out the optical components of telescope, those are only half the story. Old telescopes are often vastly improved by installing new detectors. See, it's not just how many photons are focused, it's also how many photons are detected. For centuries, the eye was the traditional detector. All the early astronomy treatises have hand drawings of seen objects. Then photography was introduced midway in the 19th century, principally by the famed British astronomer John Herschel. There's still nothing quite so satisfying, I think, as an image of one of those distant galaxies and nebula. But almost all modern telescopes rely on electronic detectors. The most advanced of these detectors can measure the signal from a single photon. That's the highest possible resolution imaginable. Now, there are many wonderful telescopes on Earth, but many astronomers see space telescopes as the real instruments of the future. You've probably heard of the Hubble Space Telescope. That provides an unparalleled view of the universe in optical wavelengths. This orbiting satellite isn't the biggest telescope, but it has a choice viewing location. It's above the Earth's atmosphere. You may recall that when the Hubble Space Telescope was first launched, it was defective. There was a horrible engineering error, and the space telescope had misaligned mirrors, and its lenses were in the wrong places, so the focus was wrong. There was a dramatic space repair mission that fixed it, and the Hubble Space Telescope is now arguably the finest telescope ever made. The last servicing mission for that telescope will take place in 2002, and the telescope is expected to perform quite well to about 2010. Well, if all goes well, the Hubble Space Telescope is going to be surpassed in 2007 by what's called the Next Generation Space Telescope. That's an instrument now planned to have a mere 8 to 10 meters across. It's a space telescope that'll have many times the light-gathering power of the Hubble Space Telescope, and it should be able to see to the very edge of the visible universe. And then, thinking much farther into the future, also in the books are two large optical interferometric telescopes. These are telescopes that synchronize their measurements of photons at two widely separated mirrors. In this way, astronomers hope to get exceptional spatial resolution. So good, in fact, it might be possible to detect planets like the Earth orbiting distant stars. So this next generation space telescope has been dubbed the Planet Finder. So in addition to this impressive arsenal of optical telescopes, there are now instruments in place that examine the universe at many, many other wavelengths. The atmosphere is largely transparent to radio waves, so radio telescopes can be ground-based. Now, because radio waves are very long wavelength, it takes a large curved surface to collect them. I'm sure you've seen pictures of these big instruments. Radio telescopes can have one very large dish. For example, the Arecibo Observatory in Puerto Rico. That telescope's actually built into a bowl-shaped topographic feature. Or they can also be composed, these radio telescopes, of an array of smaller telescopes that are linked together electronically. There's the very large array in Socorro, New Mexico. It has a Y-shaped arrangement of dishes, and you might have seen this facility in the movie Contact. All these dishes are on railroad tracks, so the baseline can be stretched out to more than 10 miles. And see, wider separation gives higher resolution. It's also proven possible to link several radio telescopes across the globe to provide a baseline of thousands of miles across. And with such a telescope, it's possible to resolve very fine features in the heavens. Now, short wavelength microwave radiation, that can also be studied from ground-based telescopes, though there's a great deal of interference, especially from communication sources on Earth. Astronomers got their first rough idea about microwave radiation from space. That was in the 1960s. They used ground-based microwave receivers to detect what's really a soft, constant microwave static. It comes from every direction in space. But more detailed studies of microwaves and lots of other wavelengths have to be conducted from orbiting satellite observatories. So much more sensitive detection of microwaves was provided by an orbiting cosmic background explorer known as COBE. That was a satellite-based observatory, and there are also new satellite microwave telescopes that includes the MAP or MAP microwave anisotropy probe. That's going to be launched in 2002. Then in 2007, there's a joint European-US microwave observatory called Planck that's going to be launched. And these satellites are going to map the slight variations in what is a very faint microwave signals that come from every portion of the universe. We're going to see in Lecture 32 that these variations provide clues about the origin of the universe. Okay, infrared observatories. They reveal warm as opposed to hot objects in the heavens. So dust clouds and young stars and brown dwarf stars, some of the coolest objects in the skies. These are really interesting, and you generally can't observe this warm matter with optical telescopes because they don't emit very much visible light. But remember the second law of thermodynamics. Heat moves from warmer to cooler places, in part by the process of radiation. Well, a warm dust cloud in space is going to radiate energy into the surrounding cold of space. That's infrared radiation. So infrared telescopes have to be in orbit above the atmosphere. Well, after all, the atmosphere is warm and it radiates infrared radiation, so you have to be above it to see it. An Earth-based infrared telescope just can't see objects in space. That's for the same reason you can't see stars during the daylight hours when the sun is out. In fact, the detectors of infrared satellites also have to be cooled. Otherwise, the detector itself would only see its own heat radiation. So, planned is the infrared astronomical satellite called IRIS. That was launched in 1983. It gave the first comprehensive view of clouds, dust clouds in the Milky Way. And that onboard detector had to be cooled with liquid nitrogen, so the satellite operated for about 9 months. Now there's a new NASA infrared telescope called SIRTIF. It's going to be launched in 2002. It's going to be placed in orbit about the sun, so it's very far from the disturbances of the Earth's atmosphere. And it's supposed to have an effective lifetime about 5 years before its cooling tanks run out. And then there's a European infrared satellite called FIRST. It's going to be launched in 2007, and I hope you're getting a sense here, this rapid pace and excitement here, the development of orbiting observatories. X-rays, they're also absorbed by the atmosphere, so X-ray telescopes have to be in a high orbit. There's the Röntgen satellite that was launched in 1990 to study the bright X-ray sources in space. Now, remember, X-rays are high energy radiation, so they point to places in space where violent events are taking place. Now, a much higher resolution X-ray data are being provided by NASA's Chandra X-ray Observatory. That was launched and deployed by the Space Shuttle Columbia in July of 1999. This Chandra is the most sophisticated X-ray observatory built to date, and it was designed specifically to observe X-rays from high-energy regions of the universe, such as remnants of exploding stars. And of course, there are several new X-ray satellites on the books. 2 proposed satellites, the European XMM, and there's a Japanese satellite, Astro-E. They're spectroscopic devices that are going to actually measure the wavelengths of these X-rays. That's never been done before. Now, the most energetic events in the universe produce bursts of gamma rays, the highest energy electromagnetic radiation. One problem is that it's really hard to focus gamma rays, so you can't always tell what direction they're coming from. There's a gamma ray observatory, the GRO, that was launched by NASA in 1991, and that detects bursts of the highest energy radiation in space. And there's a new gamma ray large area telescope, nicknamed GLAST. It's scheduled for launch in March of 2006, and that's going to pinpoint gamma ray bursts and allow astronomers to see if there's an optical or other signature to these energetic events. And after all this, I've only cataloged a few of the orbiting observatories that are being planned at this time. There's lots more information available at NASA's website. That's www.nasa.gov. It also has links to the efforts in other countries. You know, it's just an incredible time to be an astronomer or an astronomy watcher, so follow that news. Okay, now that we reviewed the nature of astronomical data and the great photon collectors of our time, we can begin to think about the stars themselves. When we turn our telescopes to space, most of what we see are stars. We can see billions of stars in the Milky Way galaxy alone. That's the collection of stars that includes our sun. And we see countless more stars in other galaxies beyond. Some systematic sense can be made of this great variety of stars on a graph of surface temperature versus total energy output. Here's what that kind of graph looks like. This is called a Hertzsprung-Russell diagram after 2 astronomers who developed it. Recall that surface temperature is determined from the spectrum or the color of the star. Blue-white stars are hotter, reddish stars are cooler. So the horizontal scale is actually plotted as 1 over temperature. down here. This is really sort of an odd convention, but it spreads out the lower temperatures where lots of interesting things are happening. So temperature actually increases on this graph from right to left. Now, the vertical axis here is the total energy output. That's determined by knowing the distance and the apparent magnitude of a star. Remember our analogy, a candle that's 10 feet away might appear to have the same brightness as a bonfire, which is 100 yards away, but the bonfire has a lot greater total energy output. So you need to know the distance as well as how bright the object appears to be. And there's another complication. Intervening dust, that's sort of like a smoky flame. It can complicate the measurement of a star's energy output. So astronomers have to correct for that effect as well. Because stars show such a wide range of energy output, that's almost 10 orders of magnitude. That's why the vertical scale of the Hertzsprung-Russell diagram is logarithmic. Each tick mark represents a factor of 10 in total energy. Now, the Hertzsprung-Russell diagram makes no assumptions whatsoever about a star's energy source, but intriguing patterns emerge as more and more stars are plotted. Here, it turns out the great majority of stars lie along a prominent curvy band down the middle here. You see that band? It's stars lying close to this line are called main sequence stars. Main sequence stars show a close relationship between temperature and energy output. Cool main sequence stars with surface temperatures at, say, 3,000 degrees, that's pretty low, they have a very low energy output, and they're down here. And then hot main sequence stars with temperatures in tens of the thousands of degrees range have up to 1 billion times higher energy output, and they're up in the other corner. Two other common groupings of stars fall well off the main sequence. In the upper right corner, over here, they're relatively cool stars that nevertheless give off huge amounts of energy. These stars have been termed red giants because the only way the cool star can give off so much radiation is to be very large. And then at the bottom of the Hertzsprung-Russell diagram, by contrast, is this group of relatively small hot stars with surprisingly low energy output. These stars are called white dwarfs because only a very small star could be so hot and yet emit relatively little radiation. The power of this Hertzsprung-Russell diagram is that it uses simple measurable properties of stars to compare and contrast the variety of stars, whether they're very close or very far away. When astronomers plot hundreds or thousands of different stars, these clear patterns emerge. That's a really powerful result. In science, you see such systematic patterns are often the key to understanding the behavior of natural systems. In a sense, then, the Hertzsprung-Russell diagram is like a periodic table for stars. All stars are systematized in a single elegant graph. So what's the nature of stars that leads to this pattern on the Hertzsprung-Russell diagram? What does that main sequence tell us about the behavior of stars? Well, spectroscopy reveals that stars begin their lives as spheres that are more than 90% hydrogen, with a small fraction of helium and a few other elements thrown in. That's true of virtually all stars. So astronomers soon realized that the main sequence stars are simply stars of all sizes that obtain their energy primarily through hydrogen fusion. That's a process called hydrogen burning. So think about how a star burns. What do you think are the relative lifetimes of a large star versus a small star? Well, it turns out that smaller stars generate less heat and pressure, so the fusion process is relatively slow. So these small stars fall in the lower right corner of the diagram. Such a small star might have a lifetime of 100 billion years. The larger stars have interiors at much higher temperature and pressure, so the fusion process is rapid. These stars occupy the upper left portion of the diagram. In fact, the largest stars are millions of times more energetic than the Sun, and they may only last for a few million years total. Now, the hydrogen fusion process takes place in 3 steps. We saw this in the last lecture. First, the 2 protons fuse and quickly undergo a beta decay to form a nucleus with 1 proton and 1 neutron. And there's also an electron and a neutrino that are emitted during this process. This is a hydrogen 2 nucleus. That's a deuterium. Then, next, a proton and a deuterium fuse to form helium 3 nucleus with 2 protons and a neutron. And then finally, 2 helium 3 nuclei fuse to form a helium 4 nucleus plus 2 protons. The net result is that 4 protons have fused to form 1 helium 4 nucleus, 2 electrons, 2 neutrinos, and lots of energy. This hydrogen burning process is well documented from a theoretical point of view, but one aspect is still not well understood. It turns out the Sun and other hydrogen burning stars must produce prodigious amounts of neutrinos. And the number of these solar neutrinos is well constrained by theory. Yet when scientists attempt to measure these solar neutrinos, they only observe about 1/3 of the expected number. This situation has been called the solar neutrino problem. Now, neutrino detection is difficult because neutrinos have no charge and they almost always pass right through matter. But there's still a big difference between theory and observation in this case. And one possible explanation is that solar neutrinos may oscillate into other particles that aren't detected. Now, particle theory says that such neutrino oscillations are only possible if neutrinos have mass. And in fact, recent experiments in the United States and in Japan are now offering convincing evidence of a neutrino mass approximately 1/1,000,000th of an electron mass. And if this is true, this discovery not only solves the solar neutrino problem, but as we'll see in Lecture 32, it also has a bearing on the ultimate fate of the universe. Well, to summarize this lecture, we've seen that astronomers collect photons. In particular, they measure 5 properties of photons: the wavelength, the intensity, the direction, the polarization, and the variation of those with time. And then these data are used to reveal 6 aspects of a star: the star's distance, its composition, its motion, its temperature, its brightness, and if you're lucky, its mass. So we have great telescopes that are both on the Earth's surface and in orbit that collect the full spectrum of electromagnetic radiation, and these data are summarized on a Hertzsprung-Russell diagram, and they reveal that most stars produce energy by the fusion of hydrogen to helium. In the next lecture, we're going to examine our Sun, which is a rather ordinary star lying midway along the main sequence of the Hertzsprung-Russell diagram. And as we'll see, the Sun and all other stars have a finite lifetime.